Okay, today we have Yogesh Joglekar. You know him, most of you, I guess, and he will talk. You changed slightly the title, no? He will talk about PT symmetry in a single oscillator with synthetic complex gauge potentials. So Yogesh, take it away.
Everybody able to hear me? Okay, I think. And then are you able to see the mouse on the screen as well? So
yes.
As I point to things. Okay, very good. All right. So thank you, Andreas and Francisco, for this really wonderful seminar series while we are all under lockdown and not able to participate in an in-person meeting. And so I have the opportunity to tell you about some of the new work that we have been doing in the field of PT symmetry. This is a work which has been done with an undergraduate student of mine, Zach Cochran, who recently graduated. Also Kaustubh Agarwal, who is a graduate student who did many of the calculations, theory stuff, as well as making figures and data analysis and things like that. Roberto Leon is a colleague of mine from UNAM in Mexico, and he has this really remarkable synthetic elements electronic platform, which made the experiments and beautiful data that I'll show you possible. Okay. Along with Alan, who is his postdoc, who did many of the experiments. So today I want to tell you about PT symmetry in a single oscillator with synthetic complex gauge potentials. And here is the outline of my talk. Those of you who know me, in recent years, I have been talking about PT symmetry in quantum platforms quite a bit, ultra-cold atoms or superconducting qubits and so on. And today I want to switch gears and talk and come back to the sort of, the original PT symmetry, which is basically where you have gain and loss, both of them being present. And so just to set the stage, I will go over some of the brief history, which many of you are experts in and very familiar with, but maybe some of the new people may not know about. And then the point I want to emphasize in all of these aspects is that traditionally, parity time symmetry has always talked about or sort of, underlaid the idea of coupling two systems, each of which has time reversal symmetry broken, but one is the time reverse version of the other. So there is a gain system and then there is a loss system. And you have two of them, you couple them, and you get PT symmetric models, basically. Okay. And then I want to ask the question of, can I get away from it? Can I get a PT symmetry in a system, a single system, which doesn't have gain or loss, at least not the way that has been traditionally thought about or implemented. Okay. And I will get to that through a really introductory physics example. This could be a freshman physics problem, or it could even be like a high school AP physics problem or something like that. Okay. And that got us thinking about this and sort of led it to this idea. And if you want to find the details, you can find it in this archive from a couple of months ago, basically. Okay. All right, so I'll talk about this example from there, present the results and experimental observations and some of the sort of distinction points from earlier works, okay, and go from there. Okay. All right, so this is a slide that many of you have seen because it's my go-to introduction slide about PT symmetry. And this is meant really for people who are not experts in the area. And so the introduction to PT theory sort of started for at least my introduction to PT theory started when I was a postdoc in Los Alamos, and I saw this paper which said complex extension of quantum mechanics from Carl and Hugh and others. And basically, when I saw that, I was just mind blown, actually, at that time. I did not understand very much, but it was really, really interesting. And so the idea was that you have these continuum models with a non-Hermitian Hamiltonian. So these are continuum models for a single particle quantum mechanics, a non-relativistic single particle on a line. So that it has a kinetic energy term, which is minus del x squared in appropriate units. And there's a potential term, which if epsilon equals 0, reaches our normal touchstone, sanity check limit, which is basically a simple harmonic oscillator. However, if epsilon is not 0, then you get this sort of range of potentials, which are complex in general, or purely imaginary sometimes, depending on the value of epsilon. And what Carl and his collaborators found numerically first in this 1998 PRL was that if I solve this eigenvalue problem on a continuum line in appropriate space in the complex X-plane, then the energy as a function of epsilon looks like this, basically. And so the key features of the Hamiltonian is that there is a Hermitian PT symmetric kinetic energy term. There's a non-Hermitian PT symmetric potential term. And this PT part, the parity and time reversal part, is why the combination I times X or functions of I times X are being used here. Under parity, X will go to minus X. Under a time reversal, I will go to minus I. And so essentially, we are considering complex functions of a combination of variables which are invariant under this combined antilinear operation. Yeah. And what was found was that the energy as a function of epsilon, basically. Yeah. When epsilon is equal to 0, we get the usual energy levels 1, 3, 5, 7, 9, and so on, basically, which are the simple harmonic oscillator level. And what was a surprise was that when epsilon is positive, then you still get real energy levels, which are bounded below, although now they are not equally spaced. Okay. And when epsilon is smaller than 0, then for any value of epsilon, you find some energy levels which are real, but beyond certain energy levels, there is a level attraction leading to an exceptional point, and the remaining eigenvalues have complex parts as well, basically. Okay. And so the general features of this kind of a Hamiltonian is what got the story started almost more than 2 decades ago. Okay. And if you do not like differential equations, if you are more comfortable with simple algebra, as many of the high school and undergraduate students are, then you can get many of these key features from just considering a simple 2x2 matrix model, which is given here. The Hamiltonian is just a J sigma X term, which is familiar. And then there is a I gamma times sigma Z term, which is essentially it's a spin in a magnetic field where one component is real, the other one is imaginary, for example. And the eigenvalues are then given by this formula, where they will become complex conjugates whenever the gamma is greater than 2j in this particular case. Yeah. And one of the key features that is different than sort of Hermitian degeneracies is that in this case, when the eigenvalues become degenerate, then the eigenvectors also do that. It's only at gamma equals 0 that the 2 eigenvectors in this case are going to be perpendicular like this. And as you increase gamma, their angle between them becomes smaller. And then eventually at gamma equals 2j, the angle is basically going to 0, or in other words, you have an exceptional point degeneracy. And that has been sort of source of a lot of interesting results in the experimental front when these kind of Hamiltonians are effectively implemented in classical systems or classical wave systems. All right, so this is sort of the introduction to how the story started. And then one of the key advances on the experimental front was made by Christodoulides and Roshhabt, who suggested that this is a system which could be realized in actually optics. So one of the challenges with the sort of the quantum formulation was what is meant by non-Hermitian Hamiltonians, or more precisely, what is meant by complex potentials, and how do we realize them? And what Dimitri realized or sort of noticed was that the Schrodinger equation for a non-relativistic particle in one dimension is isomorphic to the paraxial approximation for Maxwell equation when we consider the envelope of the electric field, which is propagating in some waveguide array. Okay. And in that case, the role of the potential in the Schrodinger equation is played by essentially local index of refraction of that waveguide. It's more specifically the index contrast, the contrast difference of the index of refraction of the waveguide versus the cladding. And this quantity can be made complex because we know indeed that the index of refraction has both real and imaginary parts. So that was in my view, sort of the insight which led to understanding that, hey, we can make complex potentials and they have some simple physical meaning. So the index of refraction having negative imaginary part, or the fact that light gets absorbed when propagating in a waveguide, is something that was well known. On the other hand, index of refraction having positive imaginary part, that would correspond to sort of a gain in the system, is something that requires more work to engineer, basically. But that really opens the floodgate. Sure.
I think you're missing this paper by Muga's group in 2005. They were the first to show that you can have PT symmetry in optics. That's like 2 years before.
Okay. Is this the JPhys A from Rashhaupt? And
yes.
Right. Yeah. That is correct. There is a JPhys A from 2005, which also proposed this, I think, which in terms of being able to use the mapping between the two. That is, yeah. So once this idea was, I guess, understood, then that really led to a floodgates of experiments being opened, because the idea was that if you have a complex potential, then gain and loss basically correspond, the imaginary potentials correspond to gain and loss. And in specific, basically, we can implement actually complex potentials through this idea. Yeah. And so once that idea was clear, then it really led to a sort of number of experiments, many of them, most of them initially led by Christodoulides, basically, in how to actually realize this in the case of various platforms. So the first one was with PT symmetry in optics, where you have two waveguides. One of them had a loss and the other one had a gain medium embedded. But the idea is so general and so beautiful of this PT symmetry that you can really just implement it in any platform in some sense, as long as you think about them as one system is lossy and therefore has a time reversal symmetry explicitly broken. And then another system is a time reverse version of that, basically. Okay. So it would be a system which has a gain in it. And if you couple those two, then at sufficiently strong coupling, you get a stabilization, if you wish. And that is what you could call as a PT restoring transition. When you start out with PT broken phases, and now you restore the PT symmetry, in particular, you restore oscillatory behavior in the system, when the coupling between these lossy and gain regions becomes strong enough. Okay. However, and so after that, there was a bunch of experiments in, for example, this was in optics. This is from Wesleyan group of Sampico-Skotas regarding the one in electrical circuits, because you have an LC circuit and it would have a resistor R. And so this LCR circuit is a damped LC oscillator. Its energy decays as a function of time. And it's coupled through mutual inductance to another circuit, which, because of an amplifier, has effectively a negative resistance. So if I look at the current curve in this oscillator when it is not coupled, the current curve in this oscillator would look like it's increasing exponentially until it saturates. So there is some limitation over which this kind of model would work, as it does for any gain medium, basically. You know, you never have a exponentially rising energy without cutoff. There would be some saturation because of nonlinearities. This idea has also been implemented also in a simple mechanical system. So literally two pendulum, basically, you know, so you have one pendulum has a resistance and it's basically going to sort of come to a stop. Another pendulum which has been pumped with energy, and you couple them and you get a stabilization when the coupling is strong. And so the basic idea is really in all of these is that classical PT corresponds to a basically having a balanced gain and loss in a system. Okay, right. And now I call it classical PT because if you try to extend this to quantum domain, then there are challenges. In the case, what have we not taken into account in this description is where the challenges lie. If you think about loss, then for any loss, we have ignored the fluctuation dissipation theorem mandated stochastic noise, whose strength will be determined by temperature. And so at finite temperature, even loss description is not complete if you just put it a negative imaginary potential, basically. That can be sort of taken care of at small temperatures, because effectively that noise terms will go to zero because its strength is proportional to the temperature. The variance of that stochastic noise is proportional to temperature. It will go to zero. With the gain process, things are more challenging. And that is because there is a quantum limit to the noise whenever you are amplifying some bosonic modes. And that quantum limit basically ensures that even at zero temperature, you would still have some quantum noise if you are going to have amplification process. In some simple picture, you can think about this in terms of, let's say, when you have a gain medium, then you are getting sort of amplification of light, and that is from stimulated emission, and it is also from spontaneous emission. And the spontaneous emission is a random process, and that would become comparable to stimulated emission if you have number of photons to be very small. So in this sense, this is a balanced gain loss picture. It works very well at in wave systems, but it presents challenges in the quantum domain, which can be overcome in some different way. But I'll not go into that today. So once you have this idea of classical PT, then here are some examples of experimental platforms in which it has been done. And the main point that I want to really bring out here is that there are always been two units. So this top left picture is actually the platform with the first paper in Nature Physics about PT symmetry, where you have in lithium niobate, you had two waveguides. One of the waveguides had a loss. The other waveguide, that loss was implemented by some ion impurities, which would absorb the light essentially. And then you had another waveguide, which had some topping basically, which worked as a gain medium. But there were two of them. Here's another paper again by Christodoulides and a company where now you had two fiber loops. But one of the loops had a loss in it, and the other loop had a gain in it by having essentially pumping the system. Okay. And then when the light goes back and forth between them, then that essentially corresponds to some sort of a PT symmetric discrete time quantum walk or discrete time walk for this particle, which has interference. This is an example where there were two micro rings, basically. One of them lossy, the other one gainy. And then when you increase the coupling between them, then that gets to have some sort of single mode lasing, whereas each of the ones has many, many modes. There have been a number of experiments by a large number of groups. This is another common setup where you have two toroidal resonators. One of them is lossy, the other one has a gain, and then there are some, I guess, transmission lines around it from which the light is put in, and you look at the results of this kind of an experiment. Okay. This is the Sampico-Skotosis experiment on the right-hand side that I'm showing, where there's a lossy unit and a gain unit. Even in the examples such as a single waveguide, you usually have an alternating arrangement of gain and loss. So this is a paper from 2011, I believe, from Alex Scherer's group, where you had a single waveguide where you had gain and loss mediums, which were in the time direction, if you wish, where you put in light from one side and it alternatively comes across gain and loss medium, basically. Okay, where the gain is usually, this is another example where there is a single cavity, but it has two modes, clockwise, counterclockwise. And those two modes, both of them, basically, one of them is lossy, the other one has gain. And the methods for implementing loss and gain are distinct, usually. So for the loss case, in the case of optics, for example, the loss is implemented by either having some sort of ions or some centers or quantum dots, which absorb that light. The other method, which is not shown here, but was pioneered by Alex Samait's group, is where instead of having some impurities within the waveguide, you just take the waveguide and you bend it in some sinusoidal manner, such that whenever you are coming across one of the turns, some of the light leaks away or couples to the continuum of modes outside of this waveguide, and that gave them a way to control loss in the system. Okay. So there are multiple methods of controlling and implementing loss in the system. On the gain front, the methods have been just laser pumping or amplification, or the other common method that has been there has been parametric amplification, basically. Okay. And so The gain media are usually harder to implement compared to loss because they also undergo saturation. And so this has been sort of the landscape of PT symmetry across pretty much all platforms, where you have one mechanism for loss and a distinct physical mechanism to implement gain. And because of that, making them balanced and completely tunable has been really challenging. So, creating a platform where I can literally tune the knob to sort of figure out a loss and a gain, or, have them vary as I want, has been really, really challenging because of these reasons. And so the question that I want to ask today and then tell you the answer about is really, how do I do that? Is there a completely different way to figure out gain and loss in these systems? And can I do it in particular in a single oscillator? Notice in all of these examples I have shown, they are usually coupled oscillators. There is a oscillator which is like a loss system, or there is a mode which is a loss system. And then there is a mode which is a gain system, which is in some physically different place or temporally different place. And then you couple them, basically. So I want to ask, can I do simpler than this? Can I do not two oscillators? Can I do one oscillator and somehow try to do PT symmetry? Okay. And the answer to that is yes. So that's the story I want to tell you about today. Okay. All right. So before we go there, though, I want to start out with the simple problem that started this for us, basically. And that is a problem of freshman physics, basically, okay? Which is why I had an undergrad student working on it for a while, Zach Cochran. All right, so here is a simple detour. It's a detour with sort of a simple example, which is just a mass and a spring system. Okay. And of course, everybody is familiar with this. So, but let me run through this, because then I want to ask a question which sort of segues into the new method that I want to talk about. All right, so for a simple mass and a spring system, this is the dynamics of it that is shown here. I stretch the mass up to this point. It has a potential energy at that time, which is 1/2 kx squared, of course. If I let the mass go, there is a force on the mass, so it picks up speed. At the equilibrium point, the kinetic energy is the maximum. It has velocity, no force, compresses the spring because of inertia, keeps going and compresses the spring. And then after that, after this compression, it moves back again kinetic energy, and you're back to this. Yeah. So everybody knows this, kinetic energy, potential energy, some is conserved, all of that, and no friction. Now, if I wanted to do PT with this, of course, one way I could do it is to introduce friction in this unit, and then make another unit which has a gain somehow, which is compensating for that friction, and then couple them, and that has been the traditional way. Instead, let me ask this question, which is written down here. What would happen to the system if I change the mass and the spring constant such that the ratio, which is the frequency of these oscillator, remains same? Okay. So I'm changing M and K such that the frequency is going to be constant. And I want to answer that question in a somewhat complicated language, and then tell you how that sort of leads to gain and loss. And because mass and spring is harder to actually implement experimentally, I'm going to switch for the rest of the talk to an inductance and a capacitance. So instead of mass and a spring system, I'm going to really talk about an LC circuit, a single LC circuit, basically. Okay. Of course, there is a one-to-one correspondence between these two that you are familiar with, but I'll just sort of focus on this model. Okay.
But Yogesh, may I ask a trivial question here?
Sure. Yeah.
So since this is a freshman physics problem, and you go to any book on analytical mechanics, and it tell you that you can multiply your Lagrangian by an overall function of time, and you will not change the equations of motion, and that's exactly what you are doing here. I can take the common factor between K and M in the Lagrangian, then I put it in front of the Lagrangian, and the equations of motion that the new Lagrangian with the time-dependent coefficient will be the same as the equations of motion of an ordinary oscillator Lagrangian. So where is the, how do you say, gospel here? What's the point?
What's the point? Okay, all right. So I guess we are, maybe have I made some mistake here? I don't think so, actually. So basically, if you are changing M and K, And the frequency is constant, essentially.
Yeah.
I'm saying basically, right? Yeah, no. So I think that the equations of, well, okay, good question. Can I come back to it,
Yes, sure,
Joshua?
sure.
Okay,
Sure.
maybe we go through this and then you see whether the question is answered or not.
Okay. Thank you.
All right.
Thank you.
Yeah. All right, so here is a simple model. Like I said, instead of the spring and a mass system, I'm going to switch to an LC circuit where things are more simpler to do, at least experimentally. Okay. All right, so here is the idea. I have an LC circuit, and I want to thank Kaustubh, my graduate student, for making these beautiful illustrations. I don't know how he does it, but he's really good at this. Okay, so I have an LC circuit. That's an inductor and a capacitor. No resistance in this circuit. I'm not assuming it to be a damped LC circuit, basically. Okay. In reality, that just means that the parallel resistance that is there is much smaller, basically, compared to whatever is the LC part, basically. Okay. All right, so I have this LC circuit. For this, the dynamics of this LC circuit is just Kirchhoff laws, which are written down here. The current through the capacitor, the current through the inductor, which is I of t, and the current through the capacitor, their sum is equal to 0, where they are defined in a way such that they have opposite signs, basically. So I of t plus this is 0. That's one of the Kirchhoff laws. That's and the second one just says that the voltage across the capacitor is the same as sort of the voltage which is across the inductor, basically, because these are ground coupled to the. So the voltage is measured from this point to that to the ground, or this point to the ground. So they are both equal. Okay, LdIdt. And this equation, which is just Kirchhoff law, can of course be written in some kind of a linear equation kind of format, where I define this phi of t as a vector, not a good vector because its elements have different units, different dimensions. This phi of t has a voltage and a current term. And the matrix then that I have on the right-hand side is going to be, of course, it will have a purely imaginary entries because I just put in an I for no reason. This is a purely real system, actually. And this is the matrix that you have. You can check that the eigenvalues of this matrix are actually just plus minus omega naught, which is the LC frequency, 1 over square root of L times C, basically. Okay, right. So this is fine. It looks like Schrodinger equation, not quite Schrodinger equation, and not really much help if you just stop at this point. Okay. But I want to try to map this system onto some kind of a Schrodinger equation-like system with properties which are Schrodinger equation-like. And so the idea is that I am going to change from this basis, which is the phi of t basis, with elements which don't have the right units, or rather elements which have different units. One is measured in volts, the other one would be measured in amperes. Instead, I will change to a basis that I called square root of energy density. And let me tell you why it is called that. So the energy in the circuit is actually a bilinear form in this case. It's just 1/2 CV squared plus 1/2 Li squared. This is all, again, basic quantum, basic introductory physics. Okay. And I can write this as this bilinear form, where now A will be just a diagonal matrix. It will have an C in one place, it will have an L in the other diagonal element with a factor of half outside. Okay, that's all, right? And now I'm going to define a psi, this new state psi, which is basically the square root of A times phi. Now, because this is energy, this is positive definite with appropriate choice of 0 of the energy always. So A will be a positive definite bilinear form. And this is a similarity transformation which goes from the state phi to the state psi, which is A raised to half times phi. Roughly speaking, if I actually look at the elements of it, it basically tells me how much of the square root of energy there is in the capacitor side and how much of the square root of energy there is on the inductor side. So in this new units, new similarity transform, if I look at state psi, then state psi has norm, which is given by the circuit energy. And if I go through this simple algebra, then what I find is that I del T of psi is equal to some Hermitian Hamiltonian, I will call it psi, where this H naught is given by omega naught times sigma y. Okay. So it just says that that would be, and until now, I haven't done anything new. I've just written all the old stuff into this format of sort of trying to change into a new basis via a similarity transformation. And this similarity transformation is not a unitary transformation. In fact, in this case, it's just a transformation which has all the real entries, diagonal entries. It doesn't have, it's not unitary. Okay. And under this transformation, the original matrix M now transformed into a Hamiltonian, which is Hermitian. And that is one way to sort of see why M has real eigenvalues, because actually, although M is not Hermitian, it has similarity transforms into a Hermitian Hamiltonian. And that Hamiltonian is omega naught sigma y. Okay. Now, sigma y basically corresponds to a purely imaginary matrix, and that's how it should be, because in the end, even if no matter what kind of new labels and all I do, this is a purely real problem. And so I better get all the answers to be purely real. The state psi must remain under evolution to be purely real, basically, just as the state phi must remain real. And so in this sort of a formalism, the unitary evolution basically just says that the LC energy is conserved. So nothing new here. It's the restatement of state norm is conserved, but I have defined the state such that its norm is the energy in the circuit. Now I want to do something different. Now what I want to do, and which is where this sort of becomes relevant, is the following. Now I want to change the capacitance and change the inductance. In other words, change the matrix A with time. And I want to do it in such a way that the product of the LC remains constant. The frequency of my circuit doesn't change, of this LC circuit, right? So if I look at this picture over here, I'll have C of t over C naught and L of t over L naught. I'm essentially surfing along this hyperbola, which is given by L times C equals constant. So I could start out with 1, 1 values, and as a function of time, I could go down this way, go up that way. But I'm only making constrained variations which keep L times C product constant, basically. Okay. So now what happens if I have this non-unitary time-dependent change of basis, okay, with this constraint? Well, you'll find, and this is again very well known in mathematics, that the equation that is obeyed by psi now, this square root of energy density vector, that equation is going to have an effective Hamiltonian. This effective Hamiltonian will have this old term that I had, and it will have a gauge term because my basis is changing from point to point. In this case, the point being in time instead of being space, but it's the same logic essentially, right? So that example is just given by so the correction is given by I del t of log of this similarity transform matrix. Okay, right. And the way I have chosen the similarity transform is such that A matrix actually has the product of the elements of A remains constant, basically. Okay, so if I do that, then this is the Hamiltonian I'm going to get. So I will get the omega. In general, I'll get omega naught of t if L and C are unconstrained variations. But I'm now going to only focus on constrained variations where L and C are varied with time, such that their frequency of my oscillator does not change. Okay. So that's sort of the key idea. Okay, so how do I do that? One of the easy way to sort of characterize that would be then that I have L of t equals L naught times some exponential function, and C of t equals C naught times the same exponential function with a minus sign in the top. So that pretty much guarantees that the product is constant, essentially. The omega naught is constant, basically. Okay? And then this f could be any function. It can be linear in time, it can be periodic, it can be aperiodic, it doesn't matter. In all of those cases, every one of those cases, I'm going to get this extra correction term from the gauge potential to be I times df dt times sigma z. So in other words, I now get a model where I have a Hermitian term, which was in a single oscillator. I have a model where I have a Hermitian term, which is omega naught times sigma y, basically. And then I have a PT symmetric term, with arbitrarily balanced gain and loss. So in other words, I could choose. So now this is the sort of dynamical PT picture on the right-hand side, where I have a function of t, f of t, which could be anything that I want. And that just means I'm surfing along this hyperbola back and forth in some different ways. And depending on my functional form of this surfing, I'm going to get a gamma of t, which could be positive, maybe turns negative, becomes positive, and so on. But the other one is exactly opposite. So I'm guaranteed to have PT symmetry. Okay. Or I'm guaranteed to have balanced gain and loss for energy, even though literally speaking, there is no resistor in the circuit and there is no sort of dissipative elements in the circuit, basically. Okay. So now this picture or this kind of gauge transformation is very well known. In fact, it has been used multiple times in different aspects, even in the PT community. In normal quantum theory, the matrix A is usually unitary because change of bases are unitary. And if I have a unitary change of basis, then its eigenvalues are on the unit circle, which means this is just a shift of energy from time to time. So in other words, this is a purely real shift that you get. Yeah. On the other hand, in the PT context, this sort of change of basis has been used to actually make non-Hermitian Hamiltonians map onto Hermitian ones when you have sort of purely real spectrum, basically. So this has also been sort of studied quite a bit. What we are doing here is a new take on this really old mathematical idea that if I change the basis, then I am going to get a gauge term if that basis change is position or time dependent, essentially. Okay. And so I get this. Now, for the most part, we are done in the sense that we have figured out a new method to implement parity time symmetry or gain and loss in a single oscillator. Okay. And it is fully sort of flexible in the sense that I can put in any form of temporal variation that I want for the inductor and the capacitor. And so now the question is, what do we do with this, or how do we show this, basically? And so this is where, so I talked to, after I sort of, we figured this out in a theory group, we talked to my collaborator, Roberto Leon, who has this amazing platform where of LC circuits, basically. So now if I really made an inductor, took a plastic pipe and wound copper wire around it or things like that, then of course I will not have an inductance which is actually doable, or it would be sort of, it's not going to be variable. Similarly, if I make a capacitance, an actual capacitance with, 2 aluminum foils with some paper in between or something like that, then that's not going to work. But instead, what we have here is a synthetic circuit, or a circuit which has synthetic elements which behave like a capacitance and an inductance in the sort of appropriate voltage ranges. Okay? So this is a complicated circuit in the sense of it has a bunch of electrical circuit elements and so on. But in the end, the bottom line is that this unit gives a response that a capacitor will give. But it also, in situ, it can be tuned. Its value can be changed dynamically with time. Similarly, this circuit gives a response that an inductor will give, basically, but it also can be dynamically changed. Okay. And then, so this LC circuit is something that Roberto has multiple units of, because they try to do sort of mimic, band structure phenomena by using electrical circuits, just as there is a movement to do that with electrical circuits or with mechanical circuits and things like that. Okay. But the main point is this is a purely Hermitian circuit in the sense that there's an L, there is a C, there is, of course, some residual R, but that is compensated, basically, effectively. And so this is a single LC circuit. So now all we have to do is consider simple examples and show that this idea works for the most part. Right? So the first example is where this function, this exponential function in the variation of L and C, this function is linear in time. That's it. F of t equals gamma of t. And then in that case, the gauge potential created gain and loss term, which is here, would be a constant. So in other words, I will get a static PT system, okay, right, in a single oscillator. And so what we do is, this is the Hamiltonian that you get. You will notice this Hamiltonian is again purely imaginary, as it should be, because in the end you want all the variables to be real. It's a classical system. It's a introductory physics circuit, really, at the heart of it. And so in fact, this actually turns out that this kind of constraint puts serious limits on what kind of Slokay Hamiltonians that you can simulate in these systems that I'll talk about later. But at this point, I have a linearly varying gamma of t, and therefore I get a prototypical PT dimer, if you wish, in a single electrical circuit, basically. So a single LC circuit, I have a prototypical LC dimer. And what is shown here, panels C, D, and E, for example, is tracking the energy or the norm of the state. My norm of the state, remember, is the energy. So tracking the norm of the state as a function of time. Okay. And when you have some value of gamma, you get some oscillatory behavior for the norm of the state. Remember, if gamma was 0, then the norm of the state, which is the energy, would be just flat because it would be undergoing a unitary evolution. When the eigenvalues are real, the evolution is not unitary, at least defined according to Dirac norm. And then in that case, the energy in the circuit, or the norm of the state, in this new basis that I talked about, square root of energy density basis, it oscillates. If I increase gamma, the oscillations become longer. The height of the amplitude also grows. The energy is about twice as much as in there. And then when you increase gamma further, this is an example where gamma is like 101% of the threshold, so 1.01 times omega naught. For this model, the threshold is at omega naught equals gamma, for example, right? Basically, okay. You see that this one grows exponentially. Well, it's not really exponential. Well, I mean, it grows exponentially at long time. In reality, it doesn't really ever happen because the elements here are going to saturate. There is only so much energy that the circuit can handle before the op-amps don't work and so on and so forth. But that's a common feature of any gain medium. It is not confined to electrical circuit. In each of these cases, there is these dotted red lines, which are the theory, and the experimental data sort of fit them fairly well. So we observe the normal PT transition in a single dimer. But the key part here is that this is an LC circuit which does not have any resistive elements basically in it, or it's not two LC circuits coupled together. It's a single LC circuit that is undergoing the PT transition. Now, another thing which I find really cool about this PT systems is that although the energy in the circuit, or the norm of the state, is not preserved in PT symmetric or PT broken region as far as Dirac norm is concerned, there are other things which are preserved. There are constants of motion in this system. Okay. And we have been studying those for a while now, trying to figure out what they are and sort of observe them in different platforms. And so for this particular system, it turns out there are two constants of motion, two linearly independent constants of motion, basically. And one of them is essentially given by just the sigma. In this case, the two constants of motion are given by sigma y, that is one, and then the other one is sigma y times the Hamiltonian. So we measure, or we extract from this data on IV the constants of motion value. It turns out the first constant of motion is identically 0 because it's proportional to sigma y. So it's imaginary part of some current voltage combinations, which is of course 0. But the other constant of motion, the eta 2, what we call, is shown here. So this is in a PT symmetric phase. The red line is the theory prediction. It's as a function of time, it is constant. In each of the cases, the red line is the theory prediction, and the gray is the data that is constructed from the experimental data, basically. Okay. Now, it is full of noise, and it is full of noise partly because this data is also full of noise because of the oscilloscope noise that is there when these measurements are done. Okay. But you can see that it is roughly flat, whereas this one fits the variation as theory predicted very well. This is in the PT broken region. In the PT broken region, remember that the energy is growing with time. Okay. So the norm of the state psi is growing with time, and yet this expectation value of this eta 2 in the same state psi remains constant as a function of time. It does have increased noise, roughly speaking, actually, and that is also because as you grow higher energy, the noise in the system increases, basically. So this is a neat example or a demonstration where in a single LC circuit, which is a static PT dimer, we have observed both PT breaking phenomenon as well as the constants of motion that are associated with this Hamiltonian, which has antilinear symmetry. I should point out that this constants of motion do not depend on system being in PT symmetric phase. They are true anywhere in the spectrum of whether the spectrum is real or complex conjugate. It doesn't matter. You always get this. Yes. And so you have this kind of a behavior. And this shows a static dimer with this synthetic platform where the L and the C values can be changed with time. So in this particular case, what was being done experimentally was that you had this system evolving, and the C, the capacitance of the system was being changed over time in this manner. Basically, that is what gave rise to, in a linear fashion, this f of t changing in a linear fashion, which is what gave rise to this static gain and loss. Yeah. All right, so now next, let me tell you about what happens if you choose this f to be periodic, because that's another domain where you get some very interesting results, generally speaking. Okay? And if I have the function f to be periodic, then you get what is called Slokay problem, because now I have a Hamiltonian which has time periodic non-hermiticity, and the behavior of the system is not described by the instantaneous eigenvalues of this time-dependent Hamiltonian, but rather by looking at what happens over one period of time of this evolution, which is non-unitary, basically. And then from there, you can either calculate the exact Slokay Hamiltonian, or you can just look at the phase diagram of the system, generally speaking. And so what is shown here are three theoretical calculations for three different functional forms f that I told you about, which are in the exponent of the L and the C. Okay. So one is where it's a sinusoidal variation for f. The other one, which is also a sinusoidal variation, but scaled with omega, so that there is a static limit that is obtained that is non-trivial in the limit omega goes to 0. And then the third one is an example where f is just piecewise constant. So in other words, it's a square wave. It sort of becomes, a constant value, switches off to its negative, again constant. So it just step-like or square wave structure, basically. Okay. And what is shown in these pictures, the vertical axis is the strength of the modulation. So sort of the strength of the function f, this prefactor alpha, if you wish. Okay. And the horizontal axis is the modulation frequency. So capital omega scaled with the relevant energy scale or the time scale in this problem, which is basically the frequency of the oscillator, which is unchanged, which we, by construction, we are keeping it fixed. Basically, these are all constrained variations of this type that we do. Okay. And so let me first go over the top figure. And the top figure shows some metric, which basically is deep blue, corresponds to PT symmetric phase, and any other color corresponds to PT broken phase. Okay. And the common feature in each of these you will see is that when you are near a frequency of 2, in other words, the ratio of 2, or capital omega equals 2 omega naught, that's the gap of the system in some quantum language, then in that case, you get that even at arbitrarily small non-hermiticity, you get PT broken region. It's present here, it's present here, it's present here. So independent of the model, this is a general feature of Slokay problems, that at resonances, you are going to get PT breaking at arbitrarily small values of gain and loss. The counterpart of it is that you will see some of these deep blue regions up here, which is to say that there are also regions where at arbitrarily large values of gain and loss strength, so the alpha value, the prefactor of this, is very high. And yet I will continue to remain in the PT symmetric phase if I'm at the right frequency, basically. Okay. So I have these kind of generic features. What's shown in the bottom panel is where instead of looking at the eigenvalues of the time evolution operator for one period, which is the Slokay time evolution operator, we look at the eigenvectors and look at the inner product to figure out where are the exceptional lines, basically. So this inner product is 0 in the Hermitian case, and the inner product goes to 1 at the exceptional points. And this is the Dirac inner product. This is not the left-right vectors inner product. This is just the Dirac inner product of the two right eigenvectors of this non-unitary time evolution operator that I'm considering. Okay. Once again, you see wherever this PT breaking happens, there are these sort of cones which basically mark out these boundaries effectively, showing that these are the places where you are getting the sort of exceptional lines. And you see there are places where there are exceptional lines coming down at fundamental frequency, but there are some which come down at other frequencies as well. And that is most clear in this square wave form. You get a resonance at 2, you get one at 2/3, which is 0.667 or so. You get at 2/5, which is 0.4, and all of those. In other words, we get this PT breaking that happens at very small values of gain and loss, okay, or the prefactor of function f. And this PT breaking occurs at very small values of this, as long as your frequency is just right. In fact, if the frequency is any of these odd resonances, then as you scan through here, you will find that you are in the PT symmetric region where the energy is oscillatory, but remains sort of, on average constant. And then there are these regions where the energy grows exponentially with time, basically. Okay, and then you increase the frequency more, and the energy is oscillatory again. Okay, so this is sort of the theoretical analysis of this model, basically. Now let's look at what the experiments show in this really cool platform where you can actually do this. So we are changing L and C with time in situ for this single oscillator. Okay? And we measure the energy in the circuit, or the state norm of this new state, what I call psi, with the change of basis. And now, instead of looking at, because we cannot measure the eigenstates and so on in this platform, in the quantum platform, we can actually measure the eigenstate or the angle between them. Here, what we do is we calculate something called amplification factor. And what is that amplification factor? Essentially, I'm going to take the energy over some time range, look at its maximum. Then I'm going to look at the energy maximum over twice that much time range. Okay? That's the ratio of the two. Yeah. If I have oscillatory behavior, this ratio will become 1, because the maximum would be the same over this time range and that time range, as long as the period is smaller than the time range, basically. Okay. On the other hand, if I have exponentially growing stuff, then this ratio would be some exponential number. And so this lambda, basically defined this way, becomes 0 in the PT symmetric phase. And it really shows the energy amplification factor, an effective amplification factor, in the PT broken phase. And all of these logic is valid as long as the period is smaller than the time window I'm taking. So in other words, this will not work very well near the exceptional lines where the period diverges. Okay, so we sort of understand that. That's fine. Yeah. All right, so now this is the function we take, f of t, which is a square wave with a certain period or a certain frequency, 1 over nu, or nu, basically. And I'll switch from angular frequency to sort of, the frequency that experimentalists use, basically, which is 1 over the time. Okay. All right. So what is shown here are experimental data for amplification factor as a function of frequency and as a function of the strength of this alpha. So my f of t is alpha times pi of t, where pi stands for this square wave function. Okay. Now I should point out, in this case, the gain and loss happen only in delta function versions, because remember, the gain loss was proportional to the derivative of f. So I only get gain and loss in this system at this point, at this point, at this point, but it needs to be taken into account because it's delta function. It always gives you finite contribution, even over infinitesimal time range, basically. Okay. Right. When you do all of that, you get pictures like this, and this really all of these sort of gray things are the theory predictions. All of the points are the experimental data. Okay. And this rich investigation is possible because you have a synthetic circuit which can be tuned in situ with all variations that you want to do. So I can vary alpha over all of these values. There is, frequency range being scanned, okay? And we are able to actually observe resonances which go from, this is the first resonance, the second, the third. So, the first resonance, which happens around 167 hertz in this particular circuit, the second resonance, nu2, the third one, the fourth one, the fifth one. So in this picture, where you cannot really see it well, 1, 2, 3, 4, 5, all of these are being observed as you scan for energy across this domain. Okay? And it's being scanned from 0.1, 2, 3, 4, 5, all the way up to here. Now, you will see that these ones seem to match very well. Andreas, can I have 5 more minutes? Okay, I'm sort of near the end of the talk, okay?
Okay, no problem.
All right, very good. So you see that this one matches very well things, but near the first resonance, this sort of skeletal, whatever grid that you see is the theory prediction. And then experimental data, you see, sort of compresses down here, right? Okay. This is the effect of gain saturation. If I have energy in the circuit growing, then eventually it will not grow exponentially, it will stop. And when it stops to grow exponentially, then that means that this metric that I'm going to use is going to get suppressed from some value down to 0, in fact, basically, because depending on what is the time window that I'm using. And so we made some model of this gain saturation on the op-amp. And when you put in that model, then this is the sort of the pink is the prediction that you get with gain saturation taken into account for what should be the value of this amplification factor. And you see that the model sort of describes it fairly well. So it sort of tells us that this is really because of gain saturation that we are getting some deviation from what would be a dome structure that would be predicted if we had infinite energy sources available, and so there was no saturation in life. So this one basically tells you this circuit, this synthetic circuit, is a really good platform. I mean, there is no example that I'm aware of which actually maps out these kind of resonances across 4 or 5 different resonances of PT transitions, basically in the Slokay domain. It's really challenging to do. We have done this with ultra-cold atoms, or we have done this with superconducting circuits. Other people have done this with electrical circuit. Portos's group has done it. But to do this with such a rich data set is possible because you have a synthetic electric circuit and because you have a single LC circuit. So the number of variables are smaller, basically. Yeah. Now, this is a Slokay dynamics. Even in this, you can figure out what are the constants of motion. There are 2 constants of motion, it turns out, in this case, because the Hamiltonian is not proportional to sigma y, just. Okay. And what is shown here is the observed constants of motion, essentially calculated one as a function of time. The yellow and the red correspond to, the yellow and the green correspond to whatever, data sets that we are referring to here in terms of resonances. We have color coded these resonances so that it's easier to refer to, the yellow one corresponds to this 3rd resonance data, or the green one corresponds to data along the 5th resonance, and so on. So everything works out fairly well. In here, the constants of motion don't work. And that is in the PT broken phase, and that is because of gain saturation effects, basically, that become relevant. If you look at it closely here, you will find that the data points are actually smaller than or lower than this surface. They're not exactly on top of the surface. Okay. Right. But all of this sort of works out fairly well. Okay. Another piece of science that you can do in this system, because it's such a simple system, is that we have an analytical formula for what these exceptional contours are. And you can park the system on the exceptional contour, and you can walk along these exceptional contours and observe the dynamics of the system. This is a 2nd order exceptional point, and so we expect the energy to grow quadratically as a function of time, basically, in the stroboscopic sense. So the TM here stands for the period evolution, basically, not stroboscopic evolution, and we expect it to do that. And so what we did was to park this system really at one of the resonances, and at each of these points calculated or experimentally measured what is the energy, basically as a function of time. So you see here are quantitative examples at alpha equals 0.2, that's up here. So it's showing you this point and that point. And one of the points, you see that the energy that is measured along the 2 points are very different. In one case, the energy is of the order of 5 millijoules, for example. Okay. On the other side, the energy is almost a factor of 6 more. Yeah. Now, this is energy as a function of time, and that's why it showed steps, because this is, continuously speaking, this system is unitary evolving, except for the places where there is a delta function gain and loss. Okay. It's only at certain periods that your system has active gain and loss. That's at a period and half of the period, and that's why you see these sort of steps that you see in here. Okay. And there's some asymmetry of this blue and red that shows up if you are walking along the exceptional contour this way or that way. Okay. Now these contours have equal slopes, actually equal and opposite slopes. We can characterize them, calculate them analytically, and all of that. But yet, when you go this way or that way, you see this giant asymmetry. And so what we do is we take this data, we fit it to this form, and extract these coefficients A and B, which characterize this growth along the quadratic growth that is expected along a 2nd order exceptional point contour. Okay. And these are the results for the coefficients A and B. And what you want to really notice that there is a x25 here, because the blue data has been magnified 25 times to fit on the same scale. So there is a giant asymmetry when there is an evolution of this energy along these symmetrical looking contours that arise with equal slopes that arise from this Hermitian degeneracy that's out here. Okay. And you can sort of explain it away based on the initial state and things like that. But it's just a cool demonstration of sort of, also looking at the dynamics that occurs on the exceptional contour. Now, staying on the exceptional contour is extremely hard, generally speaking, in these PT systems, actually. Now, in the lossy systems, it's hard because you are sort of, the decay rate is the fastest, and so the post-selection probabilities are the smallest, and so on and so forth. On the gain systems, it's hard because at the exceptional contours, you are basically getting some noise that is associated with non-orthogonal eigenstates, and so on. And so I think that it's really a cool platform which allows you to do these really nice things that can appear in here. Okay. All right. So now I think I'm near the end of my talk. Really, this is the second last slide. And so this is a quote I found, and I thought it was really cool because it sort of goes to the heart of how theoretical physicists at least think about stuff. Which is everything is a simple harmonic oscillator, and once you have got that, then everything is downward from there. And so I have this idea, which is of a simple harmonic oscillator, how to implement PT. And so now we want to look at how do we port it to different platforms, basically, right? So for example, I could imagine metamaterials where mu and epsilon are variable. Okay. So in other words, I have light propagating in a metamaterial, and when the energy is in the electric part of the system, I crank up the epsilon because that is the sort of version of capacitance in my oscillator, right? And then when the energy goes, after some little period of time, the energy goes mostly in the magnetic field, then I crank up the mu. And I'm going to get to this kind of entirely exactly the same dynamics without having any explicit source of gain or loss in the system. Okay? Maybe there are variations in the mass and spring context also possible. So now we are at a stage where, well, okay, I think maybe it would be interesting to see where all this can be leveraged or used. This idea that a non-unitary change of basis. So I come to my last slide, which is outlook. A non-unitary, what I want you to take, if there's one sort of takeaway, is that non-unitary simulatory transforms, which have been well known, actually can be reinterpreted or recontextualized to think about as if they are gain loss potentials, basically. And so we have used that insight to realize gain and loss in a single oscillator. All known previous examples have been multiple systems, two oscillators, or sort of, two electrical circuits, or two resonators, or two different waveguides, or so on and so forth. And here, this has been done in a single oscillator. And I really want to sort of also emphasize that all of this, beyond theory, all of this cool experimental stuff is possible because of the super control and manipulability that Roberto's setup has. I mean, he has a synthetic circuit, which we can change these things in situ to be able to do any of these experiments, walk along the exceptional line, span out this entire phase diagram, and so on, is amazing. So I'm very excited about this piece of work, and I thank you for your attention. So I think I'll stop and take any questions if there are.
Thank you very much.
Thank you very much, Yogesh.
Any questions, comments?
Yeah, this is Joshua again. I wish to retract my comment. It was wrong. You cannot multiply the Lagrangian by
okay.
time-dependent function. But one small comment is that your matrix M is essentially the Liouvillean of the system. So you were analyzing essentially Hamiltonian equations of motion. I mean, you could do the same for the oscillator, and then you would have the inverse mass and the K thing in the matrix. So essentially, you were analyzing the Liouvillean of the system throughout the talk.
That is correct. That is absolutely right. I mean, this is a very simple example. And like I mentioned, I mean, I think that in this field of experimental PT stuff with finite dimensional matrices, really there is nothing new under the sun, basically. So what I'm showing here on the slide is after we did this, we went around looking for what has been done. And this problem of a simple harmonic oscillator with a mass which varies exponentially has been actually looked at, but from the context of, what happens to uncertainty principle and what happens to X and P variations and things like that. So This apparently started in 1950s. There is something called Caldi-Rolla-Kanai oscillator, which basically is exactly this problem. But there they start out with the Lagrangian, and then there are questions, subtle mathematical physicsy questions, it seemed like, about whether the Hamiltonian is well defined because you have this time-dependent mass stuff and so on, and then whether the canonical commutation relations remain valid, or whether what happens to sort of the uncertainty of a wave packet of this oscillator if it is, changing with time and so on and so forth. But as far as I know, none of them sort of talked about, let's just use this to make gain and loss in a single oscillator, basically.
More comments?
Could I just a brief comment? When you are varying the electronic components of a circuit, like you're changing the capacitance or the inductance, that actually takes work. You're actually doing work on the system. Okay, so you are driving the system, and you do have a gain and loss, as you say. I mean, this you know this perfectly well, but it's a funny kind of gain and loss, because when you're changing the capacitance and changing the inductance in a circuit, you're putting energy in and out through two different pipes, you might say. Okay, so it's a peculiar kind of system. It's not just loss over here and gain over there, but you do have a loss and gain. But you're exchanging the locations of the loss and gain very rapidly. Okay, so this is something that I think your system is novel in that sense. The loss doesn't just stay over here and the gain over here; it jumps back and forth.
That is absolutely right. I mean, this is a new way to realize gain and loss, and like I guess was talking about earlier, essentially, I want to contrast it with the methods of gain and loss that have been used before, in some sense.
Right.
Because all the older methods did not, like you said, because they were localized in one place, they required then having two entities coupled to each other.
Right. So in some sense, I mean, by changing the inductance, by changing the inductance and changing the capacitance in a circuit, you are driving the circuit in the sense of a parametric amplifier. Okay, that is sort of what you're doing, but you're doing it you're changing two components at the same time. So, in some sense, I have to think about this, but you are, your pictures that you've shown us look like the kinds of, when I see your Slokay pictures, it looks like parametric amplifiers. So it's sort of a rewriting of the ideas of PT symmetry. You don't have a circuit that's functioning autonomously, but rather you are driving it from the outside in the sense that you have gain and loss, but you're jumping around where the gain is and where the loss is.
So
that is, maybe I would like to make one comment just to sort of,
Yeah.
Correct. We are putting in energy, although one thing that I would like to sort of disagree maybe or point out and comment about is that this is a protocol which is possible with or without periodic behavior. So indeed, when you are changing the LNC in an oscillatory way, then indeed this is parametrically driven and sort of Slokay behavior emerges and all of that. But the protocol itself is valid even, that's why we are able to realize a static PT Hamiltonian in here, where the only thing that is being done is the capacitance is being increased and the inductance is being decreased. That's all, basically. And that, I think, distinguishes it from it being a purely parametric amplification method, which has been used in other sort of platforms, basically, before.
Yeah, but in the oscillators you showed in the last slide, somehow you have a time dependence of the action, and it's known when you change to the Hamiltonian, then you have in the kinetic energy somehow an increase of energy, and in the potential energy a loss, or other way around. So I think Feinberg made a right comment that the Lagrangian is multiplied by a function of time, and this causes then in the energy a change in the kinetic energy and in the potential energy. It's interesting that there are still integrals of motion, yeah. But I think the idea is really behind that you multiply somehow the action with some function in time.
I think that is correct. I mean, this is not, what do you call it? So indeed, the way that the amplification, I mean, I guess there are, so what I find interesting, and I have not understood it completely yet, is in some senses this static model yet, because basically it's saying, I'm doing a variation where things are not periodic. I'm changing the mass and changing the K, for example, at a rate, but the rate at which I do it determines whether the total energy of the system oscillates or whether it starts to amplify exponentially. Because that's what this variation, if I have f which is linearly varying in time, which is how we create sort of a static PT model, then the rate at which I surf along this hyperbola decides whether I am in the PT symmetric phase or PT broken phase. But I think that's, in the case when this is being periodically done, when it's going back and forth, then it's much easier to understand in some sort of parametric language. I agree.
Federico has a question.
Hi, Yogesh. So I have a question, like more on the interpretation. So from the starting point. So I understand that from the experimental point of view, it's easier to work with one system than two, so that it's cool to have PT symmetry in a single oscillator. But I mean, I wonder, this is just a mapping of your problem into a PT symmetric system, right? Because in my naive idea of parity is that you need two subsystems at least. So, and connected to this question, in some sense, if you have any second order differential equation, you can write it as a system of two coupled first order equation, and then write some non-Hermitian Hamiltonian and stuff like that.
Well, that's the Liouvillean. That's the Liouvillean that I mentioned earlier.
Yeah, I mean, Federico, you are. I would say that yes, indeed, this is true of any classical system, basically, right? You could do this because a second order differential equation can be written into a pair of first order equations, and then by identifying whatever is the constant in this system, define some change of basis that such that the norm of this this new basis, the norm of the state gets preserved, and Hermitian Hamiltonian and all of that stuff, basically. To question what is parity here, in some sense, the parity really refers to being able to exchange L and C places in some sense. Because the parity here acts in this, or more specifically, it's not changing L and C, it's changing the energy density on the L side and the energy density on the C side, because that is what the space of this vector psi is. This vector psi basically talks about square root of the energy density on the L side and the C side. And the parity refers to being able to exchange those two, which is why this Hamiltonian that you have is just sigma y.
Okay, thanks. Now it's more clear.
Yeah.
We have a question in the chat. Are these invariants Lewis invariants? Is a question by Sarang Bosal. Okay. Short answer is I don't know, because I do not know what Lewis invariants are. But it's something we can talk about more. Yeah.
So
any more questions, comments?
I have a question which is an open one. So let's take it from where Carl stopped, and you said it's not quite parametric resonance, etc. But really, let's say I'm not using your printed circuit, this sophisticated microelectronic thing. I just take a capacitor and a coil. And now in order, let's say I decrease the capacitance, so I pull apart, I pull the two plates of the capacitor apart. I have to invest work, right? Mm-hmm. And then in order to, so that would reduce capacitance, right? If I pull them apart, it reduces capacitance. And if then I have to increase inductance. I suppose I will increase inductance if I squeeze it, right? If I squeeze the coil to make it narrower, no, so that the flux lines mm-hmm. are tightened. So I have to invest work in that as well. Is there some sort of balance which you can immediately see in doing these processes?
So I think first thing is to look at how the energy goes back and forth in the sense.
Yeah.
Sorry. Right. Energy goes back and forth because you want to do this constraint variation to keep the frequency constant.
Yeah,
right?
yeah, and of course, yes, in a correlated way, of course.
Yeah.
So.
Yeah, because, I mean, I think. Sorry.
No, because for example, if you do it exponentially, then the time dependence is just a friction term. It looks exactly like a friction term in a Newton equation.
Absolutely right. I mean, these old papers that I mentioned, they all exactly focus on this point, that it looks like if I just do this, then it looks like a dissipative system.
Yeah, for the exponential time dependence. A fixed one. Yeah.
Yeah, but they therefore interpret it only as a dissipative system, never really actually, whereas what we are sort of, this analysis tells you is that actually it's not dissipative system, it's a gain loss system. Right. It could have basically be used to either stabilize the system if the rate of this exponential increase is small enough, or it can be used to break the system in the sense of having, divergent energy.
But but you surely well know that in the case of the really dissipative system, where the friction term comes from, I don't know, molecules colliding with your oscillator, or you just radiate electromagnetic waves. So it's like an antenna, this oscillator. So in such dissipative systems, we know from 90 years ago, Bateman and later Feshbach rediscovered that you can describe the dissipative system in terms of Hamiltonian dynamics, and because you include the environment, you add the environment to the dissipative system. So once the oscillator is lossy, the environment obviously is gaining. Where the oscillator losses, the environment's gain. So you can describe, you can write a variational principle for this and represent it as a Hamiltonian. And the question is, I mean, this is all well known. It's 90 years now since that paper in 31, and the question is whether your idea can, whether we can turn it on its head and try to understand Bateman and Feshbach in this new way. That's something which looks very interesting.
Bateman is different. I mean, Bateman, you have some square of a variable, and then you associate new two variables with a problem. One where you have one variable multiplied by a function, and the same other variable you divide by a function. So of time. Here you somehow increase the area of your phase space or not.
No, but you start with the dissipative oscillator, and he for exponential time dependence, he has a dissipative oscillator.
The energy of the oscillator is somehow the area encircled in the phase space, and what you do is somehow you change the radius of this circle you make in the phase space.
But in Bateman's Hamiltonian, or more precisely in Feshbach's Hamiltonian, the Hamiltonian is not the original energy, it's something else which is conserved.
Look,
So, Joshua, could you?
In Bateman, it's like this. You somehow change from one variable to two variables. One describes somehow a oscillator which is increasing in energy, and the other somehow which is damped. This is a different philosophy.
Joshua, could you please send me those papers, and then I can have a better.
Sure.
I think there are also questions with Federico and Igor Barashenko. So, do you have a question?
Federico's question might be still old, yeah, but Igor has a new question, I think.
Yeah. Okay.
Yogesh, a simple example, an elementary example of a single entity with a PT symmetry is a Dirac field. Well, spinor field, for instance, spinor field in one dimension. It has two components, but it cannot be seen as two subsystems coupled to each other, one with gain, the other one with loss. It's a single entity. But nevertheless, under certain conditions, with a certain degree of asymmetry in the self-interaction, the spinor field becomes PT symmetric. And it's actually not unrelated from your square root of energy representation. I think there is some link to your approach.
Yeah, I mean, I think that, so I am not familiar with this work actually, Igor, but I think that in 2x2 matrices, examples of PT systems which are effectively represented by 2x2 matrices is something that is indeed true, even at sort of, even in the case of, for example, if I have a ultra-cold atom gas where you have just two hyperfine levels, those would also be described by, well, I guess whether you consider the two spin components to be a separate entity or not, it may be a semantic question. But you can have a single superconducting qubit, for example, and it is PT symmetric indeed in the 2x2 context. And in that sense, I was talking more in terms of classical wave systems, which historically have always been realized in the case of context of sort of here is a loss part of the system, and here is a gain version of it, or a time reverse version of it. And let me couple that. But you're absolutely right that there are 2x2 matrix examples that you would sort of find usually in the quantum domain, actually, or semi-classical domain. That's right.
Yeah, I was actually talking about the classical spinor field. It's just a classical partial, or rather a system of two first-order partial differential equations on the line.
Okay.
But anyway, thanks, Yogesh.
Yeah, thank you.
Federico, this seems to be a new question now? No, okay. You just don't know how to put the hand down, okay. Any more questions? Okay, maybe we can finish here. I have a last comment. I Googled your quote, if it was really a random physicist, and it seems to trace back to Sidney Coleman, actually.
Okay, then I need to change that because this was more or less, I think actually I was looking for examples of simple harmonic oscillator or pictures of them, because I wanted to okay, where else could we do this, where it is feasible to do sort of, but okay. Because that's definitely not a random physicist. So, it's Sidney Coleman. Yeah.
He was my official thesis advisor.
Yeah.
Did you hear him ever quote this?
I don't remember him ever saying that, but that is the kind of silly thing that he would say.
Yeah.
Thanks again, Yogesh.
Thank you very much.
Thank you very much. Thank you for the time. Yeah.